to Q&A. And I would like to kindly ask you to type your questions using the Q&A button that you find at the bottom of the screen in the taskbar. And I need also to inform you that we are recording tonight's webinar, and the webinar will be available in a couple of days on our YouTube channel, Italian Cultural Institute in Chicago. And we're also having live streaming on Facebook of tonight's seminar. Before, I would like to leave the screen and the floor to Professor Forte, who will also moderate the Q&A at the end of the webinar, and to Professor Daniele Rosso. Thank you very much.
Thank you very much. Good evening, everybody, and thank you for joining us today for our first webinar of the year. First of all, I would like to start thanking the Italian Cultural Institute of Chicago for co-organizing the webinar with us, and in particular, the new director of the Institute, Luca De Vito. I would like to welcome the guests of the Italian Cultural Institute, the members of iRicerca, Chicago chapter, and the members of the other local chapters of the association. Before starting, I would like just to say a few words about iRicerca. iRicerca is an international association of researchers that aims to boost the interaction and the collaboration among the Italian researchers and to communicate their research outcomes to the general audience. We founded in Chicago the first local chapter in 2017, and since then we have organized several outreaching events, all at the Italian Cultural Institute. Speakers included scientists for a variety of disciplines, including neuroscience, engineering, physics, medicine, biology, and psychology. Tonight's event is for us the first online one, given the ongoing COVID-19 pandemic. It will feature Dr. Daniele Rosso, who is also a member of the board of the Chicago chapter. Daniele comes from Emilia Romagna in Italy. He graduated from the University of Bologna and received his PhD in mathematics from the University of Chicago. He was a postdoctoral fellow at the University of Ottawa and a visiting assistant professor at the University of California at Riverside. Since 2017, he is an assistant professor of mathematics at Indiana University Northwest, where he works on representation theory. Today, we'll talk about symmetry and Platonic solids. I remind once again that all the questions can be answered to the speaker at the end of the talk. Please use the Q&A box for typing your question in. And thank you, Daniele, for being with us tonight, and you can take the floor. Thank you.
Well, thanks everyone. Thanks Eleonora for the introduction. Thanks to the Italian Institute of Culture of Chicago for giving me the opportunity to give this webinar, and in particular to the director. And thank you to everyone who decided to attend and watch this. My title is Beautiful Symmetries, the Platonic Solids, and my goal is to give an idea that mathematics can be beautiful. So often when I talk about studying mathematics or being a mathematician, people have reactions that are not necessarily positive. They think math is hard, and they maybe don't see why it's interesting. But so tonight I would like to just give a little bit of a contribution to the idea that math can also be beautiful. So I'm talking about symmetry. So what is symmetry? That's sort of the motivating question here. And I think that everyone sort of has an intuitive understanding of what symmetry is by looking at patterns in nature, okay? And I feel like that as humans, we find regular patterns, symmetric patterns in nature to be beautiful. So examples can be butterflies, right? Butterflies are symmetric and they're beautiful. And another example of something that's as a regular pattern symmetric, it can be a snowflake. So what does it mean that these objects are symmetric? Okay, so we all intuitively understand that these objects are symmetric, but what does that really mean? So let's look at the butterfly first. So what it means that it's symmetric is that, in this case, that the left side is the same as the right side, okay? So that if somehow we switch the left and right side, for example, if you put the butterfly in front of a mirror and we reflect its image, then it will stay the same. The image will remain the same because the left and the right side are the same. The same thing happens with a snowflake. If you exchange the left and right side, the image remains the same. But for the snowflake, it's even more involved in that, right? Even if you exchange the top and bottom, the figure remains the same. Or, I mean, really, the snowflakes as sort of a repeating pattern of 6 sides, they're all the same. So even if you take the shape and you rotate it around its center, you will again get the same shape again. And this is what symmetry is. So what symmetry is symmetry of an object is a transformation that leaves the object unchanged. Okay, so the example as I've given here for the butterfly and for the snowflake, right, is that the type of transformation that can be considered a symmetry is, for example, a reflection or a rotation. Okay, so the butterfly is unchanged if we exchange left and right side. So if we reflect across a mirror, and the snowflake is unchanged on that, but it's also unchanged if you rotate around its center. So these transformations are the symmetries. So now, specifically for tonight, I will focus on symmetry of certain geometric objects. So let's start looking at some symmetries of geometric shapes. Let's start with a very simple shape, a triangle. Okay, so let's take this equilateral triangle. Okay, so the 3 sides are the same. So what kind of transformation can I do to the triangle to leave the shape the same? Well, I could try to rotate. Okay, so for example, if I rotate by 60 degrees, okay, so you fix the center of the triangle, you rotate this triangle around its center. If you rotate by 60 degrees, you get a triangle that's upside down. So it's not the same shape anymore. Okay, so that's not a symmetry of the triangle. So we want a symmetry. It needs to be a transformation that leaves the object overall exactly the same. So instead, what I can do is I can rotate by 120 degrees. So to see what happens, I'm going to give numbers to the angles of the triangle. Okay, so let's call them 1, 2, and 3. So if I rotate by 120 degrees, now the triangle is still exactly an equilateral triangle like before, but the numbers have moved, right? Because when I rotate the triangle, the numbers have moved. So it's still the same triangle, but the points are in different spots. And then you can do it again. Now, if you rotate again, you're actually going to get back to where you started, but there's more symmetries of the triangle, and that's exactly when the reflections come in. As I was saying for the butterfly, we can do the same thing for the triangle, right? So we sort of divide a triangle in half and exchange the left and right sides. It's still going to be the same triangle again, except that now the 1 and the 2 have changed spots. And then from here, you can rotate again, and you rotate again, and you see that these are all different symmetries because the numbers are all in different positions. And actually, these are all the possibilities. So for the triangle, there's exactly 6 symmetries. These are the 6 possibilities. And so actually, this is a very regular shape, so it has quite a lot of symmetries. If we look at shapes that are less regular, we're going to see that we're going to have fewer symmetries. Okay, so let's look at shapes that are not as regular as the equilateral triangle. Let's take an isosceles triangle. Okay, so now 2 of the sides are the same and the other one is different. Well, now if I try to rotate this shape, well, now it's not the same triangle anymore. So that doesn't work. That's not a symmetry of my isosceles triangle. Well, let's try the reflection instead. Reflection, again, I cut it in half and exchange the left and right sides. Well, this does work, okay? This is, again, the isosceles triangle, just in 1 and the 2 have exchanged spots. So this triangle still has the reflection, but only the reflection as a symmetry. Now, if you take an even more irregular shape, like a scalene triangle, okay, so this means that all the 3 sides are different. Well, now if you rotate this one, clearly doesn't work, gives you a different kind of triangle. Or even if you try to reflect left to right, this is, again, looks different. It's not the same shape anymore. Okay, so really the scalene triangle has no interesting symmetries. So, so really what we want to see, we want to talk about symmetries, we want to talk about beautiful shapes. So we want to look at shapes that have as many symmetries as possible. So we want to look at regular shapes. So let's start looking at regular shapes that can be drawn, geometric shapes in the plane, okay? So like the triangle before. So we want to look at what they're called polygons. Okay, so a polygon, this is word from the Greek, poly means many, gon means angle, okay? So many angles. So a polygon is a shape that's drawn by drawing some points that I've denoted here by red dots, and then joining them with straight line segments, okay? So the points are called the vertices, and the straight line segments, those are the edges of my polygon. Okay, so these two examples that I've just drawn here, these are not very regular at all, right? These are all different size, angles, and sides. So these are not gonna have really any interesting symmetries. So what we want are regular polygons. So what does that mean? A regular polygon means that all the sides have the same length and all the angles are the same. So for example, here's 3 examples right here. So this is the equilateral triangle that I've just used as an example before. And then this is a square. Okay, all the sides are the same. All the angles are right angles in this case. This is a regular pentagon. Okay, 5 sides, they're all the same. And one interesting thing about the regular polygons is that if you draw a circle around them, all the vertices will be on that circle. So these shapes have a lot of symmetries, right? They have rotational symmetries, they have reflection symmetries, as we were saying before. So how many regular polygons can we draw? Well, actually, infinitely many, okay? You can draw a regular polygon with as many sides as you want, okay? And the way you can do it is that you take a circle, you divide it into equal parts, and those are gonna be your vertices, and then you just join the points to get your regular polygon. Okay, for example, the examples we've just seen, you divide the circle in 3 equal parts, and then you join those 3 points, that's an equilateral triangle. If you divide the circle into 4 parts, that's gonna be a square. You divide the circle into 5 equal parts, that's a regular pentagon. 6 parts, you get a regular hexagon, and so on. Really, just pick any number, divide the circle into that many parts, and that's gonna give you a regular polygon with that many number of sides. So for example, just pick any number. Okay, this number is 11, okay? So divide the circle into 11 equal parts, and you can join all those, and that's gonna be a regular, it's called a hendecahedron, okay? From the Greek, hendeca means 11. But really, you can pick any number, and you can get a regular polygon with that many number of sides. Now, one potentially interesting question here, and this is actually a question that was asked by mathematicians since the time of ancient Greece, is how do you draw these regular shapes, just by hand using a compass and a ruler and a straight edge? Okay, and actually that's a very interesting mathematical question that not all these regular shapes, these regular polygons can be drawn using a compass and a straight edge, okay? It really depends on the number of sides. This one right here, the regular hendecahedron with 11 sides, cannot be drawn using a compass and straight edge. You cannot get the exact length of sides if you just want to do it by hand. And there's actually, this, again, as I said, started in ancient Greece. The Greeks certainly knew how to draw the pentagon. The triangle, of course, the square, the pentagon. The pentagon actually at least was taught in school when I was in school. I don't know, maybe it's still taught in schools how to draw that. But there's actually, a very interesting mathematical theory for which ones can be done. I'm not gonna go into all the details of this because they require a lot of explanations, but it involves prime numbers. So there's a very interesting theorem due to first Gauss and then Wansel. So that's something if you want to look it up for yourself. I'm not going to focus on that for tonight. So for tonight, what I want to look at instead are regular three-dimensional shapes. Okay, so not only these regular polygons that are flat, two-dimensionals on the plane, I really am interested in three-dimensional shapes. So let's look at three-dimensional shapes. So the kind of shapes we're looking at are called polyhedra. So polyhedron, again from the Greek, many bases. So a polyhedron is really a shape which is made by taking polygons that we've just talked about and then putting them together to get a three-dimensional shape. Okay, so when you have two polygons that are joined together, that's going to give you an edge of your three-dimensional shape. That's a straight line segment. And then you're going to have vertices of your three-dimensional shape. And at a vertex, there's going to be three or more polygons that join together at that point. Okay, some examples of three-dimensional shapes that we might be interested in are a cube, a pyramid, and a prism. Right, so for the cube, all the faces are squares. For the pyramid, some faces are triangles, and the bottom face is a square. For this kind of prism, two faces are pentagons, the other faces are rectangles. And you can see, right, sort of in dark black, what's really drawn is the edges, right? That's where two faces meet. And then now I've just highlighted in red the vertices of these shapes, okay? So for example, at this vertex, there's three squares that meet there. For the pyramid, at this top vertex, there's four triangles that are all joined at that vertex. Okay, so one interesting thing about polyhedra, which is kind of surprising, is what's called Euler's formula. So I'm going to jump back and forth a little bit with history in this talk. Okay, I'm not like doing a chronological order of anything. So I'm going to jump a little bit back and forth. So now, since we talked about vertices and faces of polyhedra, I want to mention Euler's formula. So this is from Leonhard Euler, which was a Swiss mathematician, and this formula dates to 1758. So let's look at V is going to be the number of vertices of my shape, of my polyhedra. E is the number of edges, and F is the number of faces. Okay, so for example, for the cube, pyramid, and prism, I've counted them. The numbers are here, but for the cube, there's 8 vertices, right? There's 4 at the top, 4 at the bottom. There's 12 edges, right? There's 4 up here, 4 at the bottom here, and another 4 on these sides. And there's 6 faces, right? There's 6 squares that make up the faces of the cube. And then you can count them for the pyramid, for the prism. You can really count them for any polyhedron. And you would think that, these numbers could be whatever. These numbers could be anything, right? You just put a bunch of, shapes together, and then you count how many vertices you have, how many edges you have, and how many faces you have. But really, these numbers are related, okay? And that's the surprising thing that Euler's formula tells us. If you take the number of vertices of a polyhedron and you subtract the number of edges and you add the number of faces, the result is always equal to 2. You can check that it works in these examples, or if you want, you can just draw your own shape, check, and it will work. I have to say here, okay, technically there are some exceptions, but to do an exception, you'd have to create a weird shape that has holes in them, okay? So as long as your shape doesn't have any holes in it, then this formula will be true. All right, so now we want to talk about shapes that have a lot of symmetries, shapes that are regular and beautiful that have a lot of symmetries. So let's talk about regular polyhedra. Okay, so what is a regular polyhedron? Well, what that means is that all the faces should be the same, right? So all the faces should be regular polygons that should all be the same. And at each vertex, there should be the same number of faces that meet at each vertex. Okay, so that's what going to be a regular polyhedron. So let's look at the examples that we've seen, these 3 examples of polyhedra, the cube, the pyramid, and the prism. Well, according to this definition, the cube is regular, right? Because the cube is made of, the faces are all squares, the square is regular, and all the faces are the same, they're all squares. And at each vertex, there's 3 squares that meet there. Okay, well, clearly the pyramid is not regular because some of the polygons are triangles some of the faces are triangles, and other faces are square. The prism is also not regular because these faces are pentagons at the top and the bottom. The other ones are rectangles, so they're not all the same. Okay, so the cube is an example of a regular polyhedron. So now you could ask the same question that we asked before for two-dimensional shapes. Now we can ask the same question for three-dimensional shapes. Well, how many regular solid shapes are there? How many regular polyhedron are there? And you might think that maybe the answer is like the answer for polygons. Okay, maybe you just pick a number of faces or number of vertices that you want, and you're always going to be able to draw a certain three-dimensional shapes that has that number of faces or that number of vertices. But actually, the answer is no. Okay, the answer is not infinitely many. Okay, there's actually only a finite number of possibilities for regular three-dimensional shapes, and this is quite remarkable. So I'm going to try to briefly explain why this is the case, why it's not possible to have infinitely many shapes, and really what are the finite small list of shapes that we can have for regular three-dimensional shapes. And I'm going to follow basically the argument that it can be found in Euclid's Elements. Okay, so Euclid's Elements is sort of the geometry, the classical geometry book, right? So dates from approximately 300 BC. And that was really a collection of all the knowledge of geometry and even other kinds of mathematics, number theory, for example, that was known by the time of Euclid. Okay, so Euclid didn't really come up with everything that was in the Elements, but he sort of collected the knowledge of the time. For example, then this argument about the regular solids is due probably to Theaetetus, if I'm pronouncing that right, which lived from like 417 to 369 BC, so before Euclid. But it's really remarkable because then Euclid's Elements was used as a geometry textbook for like, thousands of years, okay, until the, Renaissance, until the early modern period, people were still learning geometry from Euclid's Elements. So, okay, so this is gonna be the only mathematical proof that I give in this talk. So, maybe it will be a little confusing, a little difficult to follow, but please bear with me. All right, so the argument goes like this. If we wanna have a three-dimensional shape, that's a regular shape, then at each vertex, well, you have to have at least three faces at each vertex, okay? Because if you only have two faces, that's gonna give you an edge instead. So there's gonna be at least three faces at each vertex. And now if you look at the faces that meet at each vertex, the sum of the angles of those polygons has to be less than 360. Otherwise, the shape will be flat and you would not be able to become a three-dimensional shape. Okay, this might seem a little confusing, so let me give an example of a picture here. So if we take three squares, okay, we join them at this vertex, red vertex in the middle. Okay, now if you look at the angles are right angles for a square, so it's 90 degrees. So three of them is 270. 270 is less than 360. All right, so we have a little bit of room. Okay, so, and with this room, so the way you can think of this is that if you really draw these three squares and you sort of cut them out, and then you want to fold them to make a cube, right? So since we have three squares, we can fold them a little bit and then close them off. And this becomes the vertex of a cube, okay? So we have that vertex and we have three squares and the sum of the angles is 270. If instead, if we wanted to start with four squares, okay, with four squares, the sum of the angles would be 360 because it's 90 times 4. Well, now it's impossible to fold this to make it into a three-dimensional shape, right? Because now there's no room to fold it up because it's already flat. So, right, so this is the idea. So to have a three-dimensional shape, you need to have at each vertex less than 360 degrees. So this actually limits the possibilities quite a lot. So what are the possibilities then? Which regular polyhedra are possible, which regular 3D shapes are possible. Well, let me look at this little table. Okay, so first we have to pick which shape we want our faces to be. Okay, so the faces have to be regular polygons. So they could be, for example, triangles. They could be squares. They could be pentagons. Maybe they could be hexagons, or higher number of sides as well. Well, let's look at the angles. Okay, so for the triangle, each angle is 60 degrees. For the square, each angle is 90. For the pentagon, each angle is 108. For the hexagon is 120. So on. If you want the heptagon with 7 sides, this would be even higher. Okay, but now we have to look at, so these numbers that I put in this table is just, multiply this by 3, 4, 5, 6, and 7. If we want to put that many faces around a vertex. Okay, but now we want to find which of these numbers are less than 360, right? Because what we said is that for the faces that are close to a vertex, the total has to be less than 360. Otherwise, it's going to be flat, and I'm not going to be able to make it into a 3-dimensional shape. Well, if you look at these numbers, only 5 of these, which I've highlighted in red right now, are less than 360. All the other numbers are bigger than 360. And clearly, even if you take, higher number of sides here, you're going to get higher numbers. So they're also going to be bigger than 360. Or if you take more faces, it's also going to be bigger than 360. So really, there's only 5 possibilities for regular 3-dimensional shapes. And the 5 possibilities come exactly from these 5 possibilities here. Okay, so you can have triangular shapes, triangular faces with either 3, 4, or 5 faces at each vertex, or you could have square faces, or you could have pentagonal faces. All right, so now I would like to show you what these 5 regular shapes are. Okay, so let's meet our 5 new friends here. Yeah, I guess I made this comment here. I was forgetting. There's another way that you can make this proof. Instead of using this argument, this is what Euclid's argument used to prove that there's only 5 possible regular 3-dimensional shapes. There's another way to prove this using Euler's formula, though that clearly was a proof that came out later, since Euler's formula is from 1700s. I'm not going to get into that because there's a lot of computations involved there, so I don't want to bother everyone with the computations, but if you're interested, there's another way to prove that there's only 5 regular shapes. Okay, but as I was saying, so let me show you what these 5 regular polyhedra are, and hopefully you will, like me, you will also find them quite beautiful because they're regular and they have a lot of symmetries. So the first one is the tetrahedron, tetra from Greek, so it's 4. So this has 4 faces. All right, so this is when we have 3 triangles at each vertex. So it's going to have 4 vertices, 6 edges, and 4 faces. And it looks like this. So let me do a little animation here. You can see the spinning shape. So really what this shape is, so let me pause it for a second. Maybe you can see it better like this. What this shape really is that it's a pyramid with a triangular base. Okay, so the base is an equilateral triangle, and then there's 3 other triangles on top of it that form a pyramid with it. Okay, so this is our first of the 5 regular shapes, the tetrahedron. All right, now let's go. The next one is the icosahedron, also better known as the cube. Okay, so exa from Greek 6, it has 6 faces. Okay, this is the one where the faces are squares. Okay, there's going to be 3 squares at each vertex. There's 8 vertices, 12 edges, 6 faces. Well, you all know what a cube looks like, so I don't need to spend a lot of time on this. Okay, just show you the little animation. It's a cube. All right, so let's go now to the next shape. The next shape is the octahedron. So octa means 8, so it's going to have 8 faces. So this is the one where we take 4 triangles meeting at each vertex. Okay, so there's going to be 6 vertices, 12 edges, and 8 faces. And it looks like this. All right, so this is the octahedron. And so one way, if you want to visualize this a little bit, understand what this looks like, this is really 2 square pyramids on top of each other. Okay, so if you take a square pyramid where the 4 triangular sides are all equilateral triangles and the bottom is a square, you take another one like that, and you stick the squares together, then you sort of have a pyramid going both sides, and that's what this shape looks like, okay? So this is called the octahedron. All right, let's look at the next shape. The next one is called the dodecahedron. Dodeca means 12, so this is gonna have 12 faces. So this is the one where the faces look like pentagons, okay? So there's gonna be 3 pentagons meeting at each vertex. It's gonna have 20 vertices, 30 edges, and 12 faces, and it looks like this. This is the dodecahedron, and you know, I find this shape quite beautiful. You know, it has a lot of symmetries, and you can see that at each vertex there's 3 pentagons coming together. Okay. All right, so that was our 4th shape, and then last but not least, our last friend is called the icosahedron. So icos means 20. So it's going to have 20 faces, and this is the one where we're going to have, again, triangular faces, and there's going to be 5 triangles meeting at each vertex. So this shape has 12 vertices, 30 edges, and 20 faces, and it looks like this. All right, again, I find this shape very, very beautiful. It's very symmetric. And you can see that at each vertex, there's 1, 2, 3, 4, 5 triangles coming together. Okay, so these 5 regular polyhedra, they're usually called the Platonic solids. And the reason for that is because of what I'm going to say in the next slide. So the Platonic solids, these 5 regular shapes, came up prominently in one of the written works of Plato. So they've related them to the 4 elements. So what are the 4 elements? I mean, probably everyone is familiar with this, right? The idea of the 4 classical elements that make all the structure of the universe. So the 4 elements are fire, air, water, and earth. I mean, clearly this is not the modern chemical theory, right? But this was the sort of the classical theory of the elements. In Greece, this dates to Empedocles, 5th century BC. This same idea is also found in other cultures actually throughout the world, but for the purpose of, you know, the ancient Greece, it comes to Empedocles. Well, so Plato, in his Timaeus, which is approximately 360 BC, he assigned the 4 elements to 4 of the regular solids. Okay, so this is what he writes. He writes, to earth, let us give the cubic form. For of the 4 kinds, earth is the most immobile. Of the remaining figures, the least mobile to water, the most mobile to fire, and the intermediate figure to air. And further, when we assign the smallest body to fire and the greatest to water, the intermediate to air. And again, the first in point of sharpness to fire, the second to air, and the third to water. And seeing that there still remained one other compound figure, the 5th, God used it up for the universe in his declaration thereof. Well, I mean, Plato did realize that he was associating the 4 elements with Platonic, with the 5 regular solids, but you know, there's 4 elements and 5 regular solids, so you had to come up with something for the 5th one. Okay, so maybe it's not very clear from this extract of the Timaeus which ones he means. So let me show you in the table. So, right, so he said earth is the cube, right, because it's the most solid. It doesn't move, right, because if you take all the cubes together, you know, they stack together, they fit nicely, they don't move. And really Plato thought that earth, the element earth, was made of tiny, you know, if you want what we would later call atoms, okay, all made like little tiny cubes. And he thought that fire was made of all tiny little tetrahedra, okay? So fire is the sharpest, is the smallest, so it corresponds to the smallest and sharpest shape, which is the tetrahedron. And then he thought that water was the icosahedron, and air was somewhat in the middle, was the octahedron. And this leaves out the dodecahedron, right? For the shape that somehow God used to decorate the universe. And there's a couple of different interpretations here of what that means. one possible interpretation is that the dodecahedron has 12 faces, like the 12 constellations of the zodiac signs. But other possibilities here really is that, you know, what would come later with Aristotle and then later philosophers to think that there's the fifth element, right? The quintessence, which makes up all the celestial bodies, right? So everything that's outside of Earth somehow is made of this fifth element, called by some the ether. So that will correspond to the fifth Platonic solid. So this is how the name Platonic solids came up, is really from this work of Plato, the Timaeus, and a lot of people sort of, you know, followed Plato and really considered these shapes very important because of what he associated them with the elements of the universe. Okay, so that's how they were named the Platonic solids since then. Now, one thing I wanted to mention about these shapes that I think is remarkable is duality. So what duality, the idea of duality is, if you want, the same idea, philosophical idea of the yin and the yang, okay, or the opposite but equal, you know, like two sides of the same coin. So this is the sort of the idea of duality. Something like, if you want like another expression, is like the evil twin, right? So something where like two things are sort of equal but not exactly the same, okay, equal but opposite. Two sides of the same coin, as I said. So to explain this, let me draw some pictures here. So let's start with a cube. Okay, the cube is one of our regular shapes. So what I can do is that I want to draw a new shape. And the way I'm going to do it is that for each face of the cube, I'm going to put a vertex in the middle of it. Okay, so the cube has 6 faces. I'm going to put a vertex in the middle of that. And then if the two faces share an edge, I'm going to connect those two vertices with an edge. And this is what I get. Well, now what is this new solid shape I've gotten? Well, this new solid shape I've gotten is a regular octahedron. Okay, this is really the octahedron. You can see there's, you know, the sort of two pyramids, one on top of each other. Okay, so I started with a cube, which was one of the regular shapes. I did this sort of dual procedure of turning faces into vertices, and I got the octahedron. Okay, well, but now what happens if I do the same procedure starting with the octahedron? Okay, I made it a little bigger. Okay, I'm taking the octahedron, and I'm going to draw a vertex in each of its faces. Okay, well, now that gives me 8 vertices, right? Because there's 4 triangles on top, 4 triangles at the bottom. Now, if you join them, well, maybe you see what's going to happen. If I join them, I'm going to get a cube again. So then this idea of duality, you can start with a shape, and you can sort of turn faces into vertices instead, and vice versa. That gives you another regular shape. Well, this turns the cube into the octahedron, and vice versa, the octahedron into the cube. So somehow the cube and the octahedron are two faces of the same coin. Okay, they're sort of evil twins of each other. Okay, they're the yin and the yang. And actually, this idea works for all the other shapes. Okay, not just for the cube and the octahedron. So let me draw a little table here connecting all the 5 shapes that we've seen. Right, so you can do the same game where you turn a face into a vertex, okay, and then you join them. And if you start with the tetrahedron, and you do the dual procedure, you're going to get the tetrahedron again. You start with the cube, you get the octahedron, and vice versa. And then the 2 shapes we're left with are the dodecahedron and the icosahedron, and those are also dual to each other. So if you do the duality with the dodecahedron, you're going to get the icosahedron, and vice versa. And you can see this reflected also in the numbers of the vertices and faces of all these shapes, right? Because when you do the dual, you sort of turn a face into a vertex, and vice versa. So really, you exchange the number of vertices and faces. So for the tetrahedron, you have 4 vertices and 4 faces. So when you exchange those numbers don't change. But for the cube, these numbers 8 and 6 get exchanged, become 6 and 8. And that's exactly the vertices, edges, and faces of the octahedron. And same happens with the dodecahedron and with the icosahedron. The dodecahedron has 12 vertices and 12 faces. Vice versa, the icosahedron has 12 vertices and 20 faces. Okay, and so now another thing I want to mention where these Platonic solids come up in Kepler's work. Okay, so Johannes Kepler, German astronomer, in his Mysterium Cosmographicum, so this is from 1596. So clearly Kepler knew of Plato's important, previous work. He has studied it. So what Kepler did is that he used the 5 Platonic solids to describe the orbits of the planets that were known at the time. Okay, so at the time, the known planets were Mercury, Venus, Earth, Mars, Jupiter, and Saturn. And Kepler clearly he subscribed to the heliocentric theory, right, where the planets rotate around the sun. So the way he drew them up is that he sort of fit the Platonic solids one inside the other. And you can sort of see on the left side, that's his picture of everything together. On the right side here, I have sort of zoomed in into the center so you can see it a little better. So his idea was, okay, so if you put the orbit of Mercury in the middle, and then you draw an octahedron around it, then you're gonna get the orbit of Venus outside of that, and then you can draw an icosahedron around that, then you get the orbit of Earth outside of that, then you draw a dodecahedron, then you get the orbit of Mars, and then you put a tetrahedron, then you get the orbit of Jupiter, and then you put a cube and you get the orbit of Saturn outside of that. So his this model that he proposed for the solar system, clearly he had to pick sort of the order in which to put these the 5 Platonic solids in order to get something that approximated the actual measurements that were known for the orbits at the time. And he did that in a way that sort of the orbits that would be theoretically predicted from this model, these would be as accurate as possible, but still they were only accurate up to like say 10% of the actual observations. So eventually, even though this was sort of a very beautiful theoretical model, Kepler had to accept the fact that this was not an accurate one. So he actually was the first one to propose that the orbits are not circles, but they're actually ellipses. And then he found, very important discoveries from that point of view. All right, so then to conclude, I wanted to just sort of give another sort of quick example of where you can see the Platonic solids, and where you see them, for example, in everyday life, or for some people at least. The Platonic solids can be used to make dice. Okay, so some people have games, some kind of games like role-playing games. If you've ever played like Dungeons and Dragons, for example, you would recognize these. So you can make, usual dice for games are 6-sided, okay, and those are cubes. But really, you can make dice with the Platonic solids. So you can make a dice with 4 sides, or 8 sides, or 12 sides, or 20 sides. And that is another way where you can see Platonic solids. All right, so I think that's actually all I wanted to say. And so thank you for listening. And I guess we can pass to see if there's any questions.
Thank you, Daniele. This was a very fantastic presentation. We have time for a few questions. So Nicole is asking, is the duality also related to the number of sides of a regular polygon and the number of polygons that meet at a vertex?
Yes, exactly. Yes. in fact, if you look at the dual shapes, the cube and the octahedron, the cube has at each vertex 3 squares, right? So it's 3 and 4 are the numbers. And for the octahedron is 4 triangles, right? So the numbers are 4 and 3, and those numbers have changed. So that's exactly right. What Nicole is saying is that the duality will exchange those two things. So exactly then, just like the dodecahedron and the icosahedron are dual to each other, the dodecahedron has 3 pentagons, so the numbers are 3 and 5, and then you exchange that to 5 and 3, and it becomes 5 triangles for the icosahedron. So that's exactly right. Very good.
So the next question is from Christian. Actually, it's more than one. What would change in a non-Euclidean space? Do polygons exist in non-Euclidean geometry? Is it possible to visualize them, and would we perceive them as regular? And this, I would assume we cannot perceive them as a regular.
So yes, so it is possible to talk about what it means for a shape in non-Euclidean space to be regular. I mean, so yeah, they might not be easy to visualize, but one example, for example, that you can think of is if you think of the surface of a sphere, right? So instead of sort of taking a flat plane, you can draw things on the surface of the sphere, and that's a non-Euclidean space. And you can certainly discuss what it means for a shape to be a polygon on the sphere. The way you would have to sort of change your definition is that instead of having straight line segments, if you draw things on the sphere, instead of straight line segments, you need to draw geodesics in the sphere. So the geometry is a little different, but you can certainly still discuss what it means for polygons drawn on a sphere, or the opposite of the sphere, so the hyperbolic plane. But you know, but yes, it's certainly still possible. Maybe I cannot quite well explain what it is right now, but yes, it's certainly possible to discuss polygons and regular polygons in non-Euclidean geometries.
So next question is from Joanna. Are Platonic solids recognized also in non-Western cultures?
That's a good question, and I guess I don't have a good answer to that because I would guess the answer is yes, because for example, a lot of I think a lot of the work of the ancient Greeks in geometry, for example, Euclid, was translated by the Arabs mathematicians also in the Middle Ages. So they were definitely aware of these shapes. Outside of that, I guess it's possible, but yeah, I have to admit that I don't know enough to tell you about other cultures. Sorry.
Jason asking, only some regular polygons can be drawn with a compass and a straight edge. Can you elaborate on which ones?
Yeah, so I can briefly tell you a little bit the way it works. So basically the way it works is that you need to look at the number of sides, and then you need to look at the prime factors of this number of sides. Okay, so I don't know, we learned in math at some point in school that every number can be decomposed into a product of prime numbers. So you need to look at which prime numbers appear in the number of sides. And so even numbers are okay. The only problem is for odd numbers. And the answer is that the odd numbers that appear have to be what are called Fermat primes. So as far as currently known, there's only 5 Fermat prime numbers that are currently known, although the theory is that the conjecture is there's only 5, but there could be more. And these are the numbers 3, 5, 17, 257, and 65,537. So any number that can be obtained by multiplying these numbers together, and then by multiplying by a certain power of 2, so by making even numbers, those are okay. Other odd numbers are not okay. So for example, 7 cannot be drawn, 11 cannot be drawn, 13 cannot be drawn, and a few more.
And just out of curiosity, do these 5 regular polyhedra appear somewhere else in nature or in science?
There are, you can see them in some examples, for examples in crystals, in like minerals. So as the study of rocks and minerals, you can find tetrahedra, you can find cubes, you can find octahedron. There's also like there's a mineral, the pyrite, like the sort of fake gold, fool's gold. That one has dodecahedra, although those are not exactly regular dodecahedra, but they're like kind of close. And then the icosahedron actually can be found in some examples in biology. For example, there's some unicellular like protozoa that have sort of similar like icosahedron shapes, or like some viruses actually have a regular shape that can look like an icosahedron. I believe the HIV virus kind of looks like that actually. I'm not an expert in those things, but yeah, you can find those in some other sciences.
Yeah, some herpes viruses have that structure. All right, I don't think that there are other questions, and we are running out of time. Daniele, thank you very much for being with us tonight. And I would like also to thank all the members of the Chicago chapter for organizing this webinar. And most importantly, I would like to thank everybody who attended tonight. Please stay tuned for our fall program, and I hope to see you in our future events. So good night to everybody.
So there is actually one more question in the chat, and surprisingly, I can answer to that, as we were talking earlier, because Carola Salvi is asking, how do you use this in architecture? And I cannot answer to this part. Maybe Daniele might be able to. And then, were these ever used in contemporary art? Actually, in Abu Dhabi, there is a monument called the Founders Memorial, dedicated to the memory of Sheikh Zayed, founder of the United Arab Emirates, which is constituted by the Platonic solids that are lit in the night, and they form, they are standing on vertical wires, and they are lit in the night, and they form they reproduce the image of the face of Sheikh Zayed, and I can briefly probably share my screen to show you a picture of it. Let me see. Okay. So probably now you can see it. And actually, these are the Platonic solids on your right, and the full monument on the left side. So after this surprise that I was able to answer a question in during a lecture dedicated to geometry, I would like to thank Eleonora for moderating and introducing tonight's talk, and Daniele for, let's say, taking us by the hand into this, taking a little step into this fascinating and intriguing world of geometry, and for being able to convey to all of us your passion that was clearly visible for the beauty of geometry and mathematics.
Thank you.
Thank you very much to everyone who attended this webinar, and many will follow, and especially I'm sure we'll keep on cooperating with iRicerca to discuss more topics related to science and research. Thank you very much, and have a good rest of the evening. Bye-bye.